Picture this: a single pulse of light, blazing through the endless darkness of space for 8 billion years. That's longer than Earth has existed, longer than our solar system took shape. This ancient beacon, a fast radio burst, traveled across unimaginable distances, carrying with it clues to a puzzle that has stumped scientists for decades. And when it finally reached us, it didn't just whisper its secrets, it shouted them, cracking open one of the most baffling mysteries in modern physics. What if I told you that this tiny flash of energy, fleeting as a heartbeat, held the key to understanding the very fabric of the universe? Fast radio bursts, or FRB, are some of the most enigmatic signals in the cosmos. Brief, intense bursts of radio waves that appear and vanish in milliseconds. But this one was different. It wasn't just a cosmic oddity, it was a Rosetta Stone, a message from the depths of time that helped scientists solve a question haunting them for years. Where is all the missing matter in the universe? You see, for decades, our calculations suggested there should be far more matter out there than we could actually see, and this 8 billion-year-old pulse, it handed us the answer. This is the story of how a flicker of light from the dawn of time bridged the gap between theory and reality. It's a tale of human curiosity, of telescopes pointed at the sky, and of the relentless pursuit to decode the universe's hidden language. But more than that, it's a reminder that the cosmos is always speaking to us if we know how to listen. So let's trace the journey of this extraordinary signal, from its explosive birth in a distant galaxy to the moment it rewrote the rules of physics right here on Earth. Because sometimes the biggest revelations come from the smallest, most fleeting whispers of the universe. In 2022, astronomers made a discovery that sent shockwaves through the scientific community. A telescope in Australia picked up an extraordinary signal, a fast radio burst so powerful it dwarfed anything we'd seen before. They called it FRB 2022061A, a name as complex as the mystery it carried. This wasn't just another blip in the cosmic noise. It came from a galaxy so far away, its light had been traveling for 8 billion years, long before Earth even existed. Imagine that, a split-second burst of energy, born in the ancient universe, finally reaching us like a message in a bottle washed ashore after eons at sea. What made this signal special wasn't just its age or distance. It was what happened as that radio wave raced through space. Along its journey, it passed through clouds of gas and dust, the very fabric of the cosmos. And here's the remarkable part: those clouds left fingerprints on the signal, subtle distortions that scientists could decode like a cosmic barcode. For years, astronomers had been haunted by a discrepancy. When they calculated how much matter the universe should contain, based on the Big Bang and other evidence, the numbers didn't add up. Nearly half of the expected matter was missing: no stars, no galaxies, just invisible and unexplained. But this fast radio burst changed everything. As researchers analyzed its journey, they realized those distortions held the key. The signal had interacted with matter we couldn't see, thin, scattered gas between galaxies, so diffuse it had eluded detection for decades. This was the missing piece, the hidden material that had been right in front of us all along. Think of it like trying to spot fog in the dark. You might not see it until a beam of light passes through, revealing its presence. That's exactly what this ancient pulse of radio waves did for the universe's missing matter. It illuminated the invisible, solving a puzzle that had lingered since the early days of cosmology. The implications are staggering. Not only did this discovery fill a gap in our understanding of the universe's structure, but it also showcased the power of fast radio bursts as cosmic probes. These fleeting signals, once dismissed as mere curiosities, are now proving to be some of the most valuable tools in astronomy. They're like nature's own sonar, pinging through the darkness and mapping the hidden contours of the cosmos. And FRB 202206110A. It wasn't just a burst of energy, it was a beacon, guiding us to answers we didn't even know we were searching for. For decades, astronomers faced a cosmic detective story with one glaring unanswered question: where did half the universe's ordinary matter disappear to? We're not talking about dark matter, that mysterious invisible substance that outweighs everything we can see. This was about baryonic matter, the stuff that makes up stars, planets, and even us. The math was clear. Based on the afterglow of the Big Bang and other cosmic measurements, there should have been about twice as much of this ordinary matter as we could account for. It was like meticulously inventorying a warehouse, only to find half the goods had vanished without a trace. The leading theory, that this missing matter was hiding in the vast, empty stretches between galaxies, threads of incredibly thin, hot gas, so diffuse they'd be nearly impossible to spot with traditional telescopes. Imagine trying to find a single wisp of steam in an empty stadium, but without proof, it remained just a hypothesis. That's where fast radio bursts changed the game. When FRB 202206110 streaked across the cosmos, it did something extraordinary. As that pulse of energy traveled through space, it didn't just move through emptiness, it interacted with the very material scientists had been searching for. Here's how it worked. The burst's radio waves slowed slightly as they passed through ionized gas, leaving a telltale smear in the signal's frequencies. By measuring this distortion, astronomers could calculate how much matter the waves had encountered, and the results were astonishing: the exact amount needed to fill the gap in their calculations. It was as if the universe had left breadcrumbs in the static, and this ancient light pulse finally showed us how to follow them. But why was this so hard to detect before? Think of the universe's large-scale structure like a spiderweb, with galaxies clustered at the intersections and nearly invisible filaments stretching between them. These filaments contain gas so hot and spread out that it doesn't emit light we can easily observe. Traditional methods of spotting matter, like looking for the glow of stars or the shadows of dust clouds, were useless here. The beauty of fast radio bursts is that they don't rely on light or heat. They're cosmic messengers carrying encoded information about everything they pass through. This discovery didn't just solve a decades-old mystery, it opened a new window into studying the universe's architecture. Suddenly, we had a tool to map the invisible scaffolding that connects galaxies, the hidden rivers of matter flowing through the cosmic void. And perhaps most remarkably, it showed that the answers we seek are often written in the faintest whispers of the cosmos, if only we develop the right tools to listen. Light carries more than brightness, it holds stories. Every beam racing through the cosmos is a detective, collecting clues about the places it's traveled. When that 8-billion-year-old fast radio burst finally reached Earth, it wasn't just delivering energy, it was carrying a forensic record of its journey. Scientists could read its signal like a cosmic fingerprint, uncovering traces of the very thing they'd been searching for, the missing matter woven between galaxies. Here's the magic of how light reveals the universe's secrets. As the radio waves from the burst traveled through space, they didn't move in a straight, undisturbed line. Instead, they brushed against clouds of ionized gas atoms stripped of their electrons, so thin they're practically invisible. These encounters left subtle marks on the signal, tiny delays and distortions in different frequencies. It's like shining a flashlight through mist. The beam doesn't just illuminate, it picks up the fine details of what's in its path. By studying these distortions, astronomers could measure exactly how much matter the light had passed through, and the numbers matched the missing pieces of their cosmic inventory. What makes this so revolutionary is the scale of what we're detecting. The gas between galaxies isn't just sparse, it's so diffuse that a single cubic meter might contain only a few atoms. Trying to spot it directly would be like listening for a whisper in a hurricane, but light doesn't just show us what's there, it amplifies the invisible. The fast radio burst acted like an ultra-sensitive probe, magnifying the faintest traces of matter through the subtle changes in its signal. It's a technique called dispersion measurement, and it turned this fleeting burst into one of the most precise scales ever used to weigh the universe. This discovery does more than fill a gap in a textbook. It changes how we explore space. For centuries, astronomy relied on what we could see: stars glowing, galaxies spinning, dust clouds blocking light. But now, we're learning to read the universe by what light carries with it. Fast radio bursts are just the beginning. Imagine what else we could uncover by studying how light bends, slows, or scatters on its way to us. Every photon becomes a witness, every wavelength a clue. And as we train our telescopes to listen more closely, who knows what other hidden truths the cosmos might reveal? The beauty of this breakthrough isn't just in solving a mystery, it's in realizing how much we've yet to learn. Light has been carrying these stories since the dawn of time. We're only now beginning to understand the language. Fast radio bursts are like the universe's flashbulbs, blindingly bright, impossibly brief, and capable of illuminating corners of space we never knew existed. While their origins still spark fierce debate among astronomers, one thing is certain: these cosmic flares are rewriting the rules of how we study the cosmos. Picture a magnetar, a neutron star so dense a teaspoon of its material would weigh 1 billion tons, wrapped in a magnetic field trillions of times stronger than Earth. When these stellar powerhouses twitch or crack, they might unleash the energy of 1 billion suns in milliseconds, potentially creating the perfect engine for FRBs. But not all bursts fit this mold. Some repeat at irregular intervals, others flare once and vanish forever. A few even pulse with patterns that look almost artificial, sparking wild speculation before more mundane explanations emerge. What makes these mysteries so valuable isn't just their spectacular origins, it's what they reveal as they travel. Each burst that races through intergalactic space becomes a scientific probe, its radio waves distorted by every wisp of gas, every invisible magnetic field it encounters. The FRB we've been following, the 8-billion-year-old messenger, didn't just help find missing matter. It proved these signals can map the universe's skeleton. Think of it like echolocation on a cosmic scale. Just as bats navigate by listening to how their calls bounce back, astronomers now use FRBs to trace the universe's hidden structures. When a burst passes through galaxy clusters or dark matter halos, subtle changes in its signal reveal details no telescope could see directly. Some bursts even get lensed, bent by gravity's pull, exposing otherwise invisible objects along their path. It's as if the cosmos handed us a flashlight that only illuminates what we need to study. The real revolution lies in how versatile these tools are becoming. Beyond mapping matter, FRBs help measure the universe's expansion rate independently of other methods, offering fresh perspectives on the Hubble tension, the puzzling discrepancy in cosmic growth measurements. They've even been proposed as natural timekeepers to test Einstein's relativity across billions of light years. All this from phenomena we didn't even know existed until 2007. What's astonishing isn't just how much we've learned since then, it's how much remains undiscovered. Every new burst brings surprises, whether it's an unexpected location, an unusual polarization pattern, or a baffling energy signature. Somewhere out there, another FRB might be racing toward Earth right now, carrying answers to questions we haven't thought to ask yet. And when it arrives, our telescopes will be waiting, ready to decode the next chapter in this unfolding cosmic mystery. To grasp the sheer scale of this signal's journey, let's rewind 8 billion years back to when the universe was still in its cosmic adolescence. The galaxies were closer together, the cosmos more turbulent, and our solar system wouldn't exist for another 3 billion years. It was in this ancient era that a cataclysmic event, perhaps a collapsing star or colliding neutron stars, released a blinding flash of radio waves. In less time than it takes to blink, that pulse began racing outward at the speed of light, carrying with it a snapshot of the universe as it existed when Earth was just a possibility waiting in the distant future. As the signal traveled, it became a time capsule, weaving through an ever-expanding tapestry of galaxies and cosmic structures. Picture it darting past newborn star clusters, skirting the edges of swirling nebulas, and slipping through tendrils of gas so thin they'd make Earth's atmosphere seem dense by comparison. Each encounter left its mark, a slight delay here, a subtle frequency shift there, like a traveler collecting stamps in an intergalactic passport. For context, by the time this light pulse had crossed just 1% of its journey, dinosaurs hadn't even appeared on our planet yet. The most mind-bending realization: we're not just observing distant space, we're observing distant time. When astronomers captured this signal, they weren't merely looking across space at something 8 billion light-years away. They were peering 8 billion years into the past, witnessing an event that occurred before Earth's continents had formed. It's as if the universe preserved this burst in cosmic amber, letting us study a moment frozen when the cosmos was radically different. What makes this voyage extraordinary isn't just its duration, but what it reveals about light's role as history's messenger. Unlike sound or physical objects, light doesn't degrade over these unimaginable distances. That original pulse remained pristine, its information intact, even as it passed through regions of space where temperatures swing from near absolute zero to millions of degrees. This reliability turns every photon into a potential historian, carrying data across epochs with perfect fidelity. Consider this too: while the signal was en route, the universe itself was transforming. The space between galaxies stretched, dark energy accelerated the cosmos expansion, and entire generations of stars lived and died. Yet through all that change, this faint whisper of radio waves kept traveling undeterred until our technology finally became sensitive enough to catch it. That we can intercept such ancient messages speaks not just to human ingenuity, but to the universe's remarkable transparency, its willingness to let even the faintest signals traverse the eons undisturbed. This is the magic of astronomy at its finest. We're not bound by Earth's timeline or limited to studying only what exists in our celestial neighborhood. With tools like radio telescopes, we can reach back across cosmic history, collecting stories written in light long before humans walked the Earth. And somewhere out there right now, another pulse from another era might already be on its way, carrying secrets we won't discover for billions more years. The Australian Square Kilometre Array Pathfinder, or ASCAP, isn't just another telescope, it's a cosmic eavesdropper tuned to the universe's faintest whispers. When that 8 billion-year-old fast radio burst finally reached Earth, this sprawling network of 36 dish antennas in the Australian outback was waiting. Unlike traditional telescopes that focus on capturing light, ASCAP specializes in detecting the subtlest distortions in radio waves, the kind that most instruments would miss entirely. Picture throwing a stone into a still pond. The ripples tell you not just where the stone landed, but whether it passed through leaves or branches on its way down. That's precisely what ASCAP did with this ancient signal, decoding its journey through the cosmos like a forensic scientist analyzing a bullet's path. Here's where the real magic happens. As the radio waves traveled through space, they didn't move uniformly. They slowed ever so slightly when passing through ionized gas, with higher frequencies arriving a fraction of a second sooner than lower ones. This effect, called dispersion, might sound negligible, but for astronomers, it's a treasure trove of information. By meticulously measuring this frequency-dependent delay, a technique known as dispersion measure analysis, scientists could calculate exactly how much matter the signal had encountered along its epic journey. Think of it like measuring how much a glass prism bends different colors of light to determine the material's density, except on an intergalactic scale. The precision required for this measurement is staggering. We're talking about detecting time differences smaller than a millionth of a second across signals that have traveled billions of years. ASCAP's secret lies in its phased array feed technology, essentially giving each antenna a panoramic view of the sky while maintaining incredible sensitivity. When combined with advanced signal processing algorithms, this setup can tease apart the faintest imprints left by intervening matter, much like how a fingerprint analyst enhances latent prints invisible to the naked eye. What emerged from this analysis was nothing short of revelatory. The dispersion measurements showed clear evidence of extremely diffuse gas, exactly the type theorists predicted would account for the missing matter. These intergalactic filaments, though nearly invisible, contain enough collective material to solve the decades-old discrepancy. It's as if we've been trying to weigh a cloud by staring at it, only to realize we needed to measure how much it dimmed a distant light source instead. This breakthrough extends far beyond solving one cosmic accounting problem. The same techniques can now map the universe's large-scale structure in unprecedented detail, tracing the web of gas that connects galaxies like dew on a spider's silk. Future telescopes, like the full square-kilometer array currently under construction, will turn this method into a standard tool for cosmic cartography. Every new fast radio burst detected becomes another data point, another strand in our growing understanding of the universe's hidden architecture. Perhaps most remarkably, this discovery showcases how modern astronomy often advances not by building bigger lenses, but by developing smarter ways to interpret the signals we capture. The answers were always there, encoded in the light. We just needed the right tools to listen. Finding that missing matter wasn't just about solving a cosmic accounting error. It was like discovering the invisible glue holding our understanding of the universe together. For years, the standard model of cosmology, our best blueprint for how the cosmos works, predicted that certain amounts of ordinary matter should exist. But when observations came up short, it left scientists grappling with an unsettling possibility. What if the model itself was flawed? The detection of these diffuse gas filaments didn't just fill a gap, it confirmed that the fundamental rules we've been using to decode the universe are, in fact, startlingly accurate. Think of it like building a puzzle where half the pieces were transparent. You could see the edges fitting together, but without those missing pieces, you'd never be sure the picture was complete. Now, with this discovery, we've finally found those elusive fragments, proving the puzzle was right all along. This matters because cosmology isn't just about mapping stars, it's about tracing the universe's story from the Big Bang to today. Every galaxy, every wisp of gas is part of that narrative, and if whole chapters were missing, we'd risk misreading the plot entirely. The implications ripple outward. Take galaxy formation, for instance. Without accounting for this intergalactic gas, simulations of how galaxies evolve never quite matched reality. Now, with these filaments included, the models snap into focus, revealing how matter flows into galaxies, fueling star birth and shaping cosmic structures over billions of years. It's like finally hearing the bass line in a symphony suddenly. All the other instruments make sense, but perhaps the most profound takeaway is what this says about our methods. For decades, astronomers relied on light-emitting objects to map the cosmos, which meant we were only seeing part of the picture. This discovery proves that sometimes the universe's secrets aren't hidden in what shines there in the shadows, the empty spaces, the distortions in signals racing across the void. It's a reminder that progress in science often comes not from discarding old theories, but from finding smarter ways to test them. And let's not overlook the bigger philosophical win. In a universe that constantly defies intuition, where dark energy accelerates expansion and dark matter outweighs visible stuff 5 to 1, it's reassuring to know that at least some of our predictions still hold. This isn't just a victory for astrophysics. It's a testament to human curiosity's power to unveil truths buried in the fabric of space and time. The cosmos, it turns out, has been playing fair all along. We just needed the right tools to see the whole game. Detecting a fast radio burst is like trying to catch a lightning strike with a butterfly net. You need the right tools, impeccable timing, and more than a little luck. These cosmic flashes pack the energy of hundreds of millions of suns into bursts shorter than the blink of an eye, vanishing before most telescopes can even swing into position. Their randomness adds another layer of challenge. Unlike predictable celestial events like eclipses or comet flybys, FRBs don't follow schedules or maps. They could erupt anywhere in the sky at any moment, leaving astronomers to scan the heavens like detectives staking out a suspect who might never show. The technology required to spot these elusive signals pushes the limits of modern engineering. Traditional telescopes, designed to track slow-moving objects or steady light sources, simply aren't built for millisecond phenomena. Imagine trying to photograph a speeding bullet with a camera set for long-exposure landscapes. You'd end up with a blur or nothing at all. That's why instruments like ASCAP had to reinvent how we listen to the cosmos. Instead of focusing on a single point, these arrays monitor vast swaths of sky simultaneously, processing data in real time to flag anomalies before they disappear. It's the astronomical equivalent of having thousands of microphones spread across a concert hall, each tuned to catch a single, unpredictable note. Even with cutting-edge hardware, collaboration is key. FRB hunting has become a global effort, with observatories from the Australian outback to the Canadian prairies sharing alerts across continents. When a burst is detected, every available telescope swivels to its coordinates, racing to capture follow-up observations before the trail goes cold. This networked approach turned what was once a needle in a haystack search into a coordinated cosmic dragnet. The detection of FRB 202200610 wasn't just a triumph of technology. It was proof that when scientists unite across borders, they can solve puzzles no single team could crack alone. But perhaps the greatest hurdle isn't technical, it's statistical. For every FRB we catch, thousands likely slip past undetected. The universe is vast, and our telescopes still only sample fractions of the sky at any given moment. It's like trying to predict when and where a single firefly will blink in a forest the size of a planet. That's why each successful detection, especially one as ancient and impactful as this 8-billion-year-old burst, feels like winning the cosmic lottery. What makes these challenges worthwhile is the payoff. Every FRB captured adds another piece to the puzzle, whether it's mapping missing matter, probing galaxy formation, or even testing the fundamental laws of physics. The difficulty isn't a barrier, it's a filter, ensuring that only the most resilient and innovative approaches succeed. And as our tools grow sharper and our collaborations tighter, we're not just waiting for the next burst. We're building a net to catch the universe's whispers, one fleeting flash at a time. The hunt for fast radio bursts is accelerating into an unprecedented era of discovery, with next-generation telescopes poised to transform these cosmic anomalies from mysteries into powerful tools for exploration. At the forefront stands the Square Kilometre Array, or SCAR, a revolutionary observatory now under construction across 2 continents. When completed, this mega telescope will combine thousands of dishes in South Africa with a forest of radio antennas in Western Australia, creating a collecting area equivalent to 1 square kilometre. That's not just an upgrade, it's a quantum leap in sensitivity, capable of detecting FRBs from the very edge of the observable universe. What makes SKA truly game-changing is its ability to not just spot these fleeting signals, but dissect them in real time with surgical precision. Current instruments might catch a handful of bursts per year. SKA could detect dozens daily, each pinpointed to their host galaxies with astonishing accuracy. Imagine having grainy black and white photos of lightning strikes, then suddenly switching to ultra-high-definition video that shows every branching path. This resolution will finally let astronomers match FRBs to specific cosmic environments, whether they originate from magnetars, colliding neutron stars, or phenomena we haven't even imagined yet. But the real magic lies in how SKA will use FRBs as universal probes. Every burst that passes through intergalactic space carries encoded information about the material it traversed, the cosmic equivalent of a CT scan. With enough samples, scientists could build 3-dimensional maps of the universe's large-scale structure, tracing the distribution of both ordinary and dark matter across billions of light years. It's like suddenly having X-ray vision for the cosmos, revealing hidden scaffolding that's been invisible since the dawn of astronomy. The implications ripple across multiple fields. For cosmologists, FRBs offer an independent way to measure the universe's expansion rate, potentially resolving the ongoing debate about the Hubble constant. For particle physicists, they might reveal properties of dark matter through subtle interactions with radio waves. And for theorists studying quantum gravity, these bursts could provide the first experimental tests of how space-time behaves at the smallest scales, all because their ultra-precise timing acts as a natural stopwatch across cosmic distances. Beyond SKA, an entire ecosystem of complementary instruments is emerging. Projects like CHIME in Canada and FAST in China are already expanding our FRB catalog, while space-based detectors could soon eliminate atmospheric interference entirely. Together, they're weaving a global net to catch these elusive signals, each new detection adding threads to our understanding. The coming decade promises something remarkable, a shift from simply observing FRBs to actively using them as tools, turning cosmic accidents into intentional experiments. What began as a baffling anomaly in radio telescope data is blossoming into an entire branch of astronomy. Just as X-rays revolutionized medicine by revealing our inner anatomy, fast radio bursts are giving us a way to see the invisible framework of the universe itself. And with every technological advance, we're not just getting better at finding these flashes, we're learning how to read the stories they carry across time and space. Fast radio bursts have already proven their worth by revealing the universe's missing ordinary matter. But what if these cosmic flashes could also help us tackle the even bigger mysteries of dark matter and dark energy? These two invisible forces make up 95% of the universe's total content, yet we know almost nothing about their true nature. That's where FRBs might just rewrite the rules again. Unlike traditional telescopes that rely on light, these bursts interact with the fabric of space itself, offering a backdoor to studying phenomena that have eluded detection for decades. Take dark matter first, the invisible scaffolding that holds galaxies together. We know it exists because of its gravitational pull, but it doesn't emit, absorb, or reflect light, making it nearly impossible to study directly. However, when an FRB's radio waves travel through regions rich in dark matter, subtle distortions could appear in the signal. Some theories suggest dark matter particles might interact weakly with photons, causing minute delays or scattering patterns. It's like trying to detect a breeze by watching how it bends a candle's flame, except here, the flame is a pulse of energy that's crossed billions of light years. Researchers are already designing algorithms to sift through FRB data for these telltale fingerprints, hoping to catch dark matter in the act of bending the rules of physics. Dark energy, the mysterious force accelerating the universe's expansion, presents an even thornier challenge, but FRBs could serve as cosmic yardsticks. By comparing bursts from different distances, scientists can measure how the expansion rate has changed over time, a key to understanding dark energy's behavior. Imagine the universe as a rising loaf of raisin bread, with galaxies as the raisins. FRBs give us snapshots of how fast those raisins are moving apart at different eras, letting us reconstruct the loaf's expansion history with unprecedented precision. What makes this approach groundbreaking is its independence from other measurement techniques. Current dark energy estimates rely on supernova or galaxy surveys, methods that come with their own uncertainties. FRBs provide a clean, direct probe, one that's unaffected by dust or stellar evolution. Early analyses using the dispersion of FRB signals already hint at discrepancies in cosmic expansion rates, potentially pointing toward new physics beyond our current models. The most exciting prospect, combining FRBs with other cutting-edge tools like gravitational wave detectors. A single event, say, a neutron star collision that produces both gravitational waves and an FRB, could let astronomers triangulate the universe's expansion in multiple ways simultaneously. It's the equivalent of cross-checking a map with a compass and a GPS, ensuring we're not being led astray by hidden biases in our instruments. Of course, challenges remain. We'd need thousands of well-localized FRBs to build robust statistical models, something next-generation telescopes like the ASCAP aim to provide, but the potential rewards are staggering. If FRBs could even partially illuminate the nature of dark matter or dark energy, it would rank among the greatest breakthroughs in modern cosmology. After all, solving the missing baryonic matter puzzle was just the appetizer. The main course of cosmic mysteries is still waiting to be served, and fast radio bursts might just be the perfect tool to help us dig in. Imagine trying to find a single unique snowflake in a blizzard. That's the challenge astronomers face when hunting for fast radio bursts in the ocean of cosmic noise. Traditional methods of scanning telescope data would take scientists years to manually analyze what modern algorithms can process in days. This is where artificial intelligence steps in, transforming the way we uncover the universe's secrets. Machine learning models, trained to recognize the distinct fingerprints of FRBs, now comb through petabytes of radio wave data with superhuman precision, spotting signals that even the most eagle-eyed researchers might miss. The process starts with raw data, endless streams of radio frequencies captured by telescopes like CHIME or ASCAP. Buried in this chaotic static are the telltale spikes of FRBs, fleeting signals that last mere milliseconds. Early attempts to identify them relied on simple threshold triggers, flagging anything above a certain noise level. But this brute force approach produced countless false positives: radio interference from satellites, atmospheric disturbances, even microwave ovens near observatories could mimic an FRB. AI changed the game by learning the subtle differences between artificial noise and genuine cosmic events. Neural networks trained on thousands of confirmed bursts now detect patterns imperceptible to humans, like the specific way an FRB's frequency drifts over time or its unique polarization signature. What makes this synergy revolutionary isn't just speed, it's adaptability. When astronomers discovered repeating FRBs, machine learning models were quickly retrained to prioritize these unusual signals. As new telescope arrays come online, the algorithms evolve in tandem, optimizing their search strategies for each instrument's unique characteristics. It's like teaching a musician to recognize a single note played on different instruments, whether it's a violin, piano, or distant galaxy. The AI learns the essential melody beneath the noise. The impact extends beyond detection. Once an FRB is found, AI helps trace its origin by analyzing how the signal disperses, a clue to how much matter it traversed. Advanced clustering algorithms group bursts by similar traits, hinting at common origins or propagation paths. Some teams are even using generative AI to simulate FRBs under different cosmic conditions, testing theories about their sources without waiting for new observations. This feedback loop between discovery and simulation accelerates progress exponentially, turning what was once a needle in a haystack search into a systematic exploration. Perhaps most exciting is how these tools democratize astronomy. Cloud-based AI platforms allow researchers worldwide to analyze telescope data without needing supercomputers, leveling the playing field for smaller institutions. Citizen science projects harness crowd-sourced AI training, letting volunteers classify potential FRBs from their home computers. Together, these advances mean we're not just finding more bursts, we're building a living, learning system that grows smarter with every new discovery. The marriage of AI and astronomy isn't about replacing human curiosity, it's about amplifying it. By automating the tedious, these tools free scientists to focus on the profound questions: what creates these bursts? Why do some repeat while others vanish? What else might they reveal about the universe's hidden scaffolding? The answers are out there, racing toward us at light speed. And now, thanks to artificial intelligence, we're finally learning how to listen. When the discovery of the missing matter finally hit the scientific press, it sent ripples through laboratories and lecture halls worldwide. Theoretical physicists who had spent their careers calculating the universe's hidden structure suddenly saw their equations leap off the page and into reality. Cosmologist J. Xavier Prochaska, part of the team that analyzed the historic FRB, described the moment as like watching fog lift suddenly. The landscape we knew was there became visible. Social media buzzed as researchers who'd spent decades debating the missing baryon problem in specialized journals found their niche topic trending alongside celebrity news. The media frenzy was impossible to ignore. Major outlets ran headlines like "Cosmic Detective Work Solves 8 Billion-Year-Old Mystery" and "Astronomers Find Universe's Lost Matter Using Ancient Light." Science communicators scrambled to explain dispersion measures and ionized gas filaments to curious audiences, with some creative analogies stealing the show. One viral TikTok compared the discovery to realizing your wallet wasn't actually missing. It had just been hiding in the lining of your coat all along. Planetariums updated their shows overnight, weaving the breakthrough into narratives about the cosmic web, while educators added fresh case studies to astronomy syllabi. What made this reaction so intense wasn't just the scientific significance, it was the rare clarity of the story. Unlike abstract concepts like dark energy or string theory, this was a tangible puzzle with a satisfying resolution. The public could grasp the essential idea. Scientists predicted X amount of stuff should exist. They couldn't find half of it, and now a burst of ancient light had revealed where it was hiding. Even children understood the thrill of the cosmic scavenger hunt. Behind the scenes, the validation extended beyond astronomy. Particle physicists saw confirmation that their models of ordinary matter were correct, while engineers who designed the radio telescopes basked in the spotlight. The discovery became a rallying cry for big science projects, proving the value of patient, collaborative research. Funding committees suddenly had a poster child for why investing in next-generation observatories wasn't just academic, it was key to unlocking the universe's deepest secrets. Perhaps most telling was how the news reignited interest in basic science. Universities reported spikes in physics program applications, and public telescope sales surged as amateur astronomers sought to connect with the cosmos that had just become a little less mysterious. In an era often dominated by division, this breakthrough offered something rare, a moment of collective wonder, a reminder that the universe still holds stories waiting to be decoded, and that every one of us is part of the audience. The cosmos speaks in many languages. Some shout, some whisper, and some, like fast radio bursts, leave cryptic messages etched in radio waves. But FRBs aren't alone in their mystery. Take gamma-ray bursts, for instance. These colossal explosions unleash more energy in seconds than our sun will emit in its entire lifetime. While both phenomena are fleeting, gamma-ray bursts trace violent deaths of massive stars or neutron star collisions, whereas FRBs could arise from magnetar tantrums or cosmic collisions we've yet to imagine. What sets them apart isn't just their energy, it's what they reveal. Gamma-ray bursts illuminate the universe's most cataclysmic events, while FRBs expose the quiet, hidden highways of gas between galaxies. Then there are pulsars, the universe's precision timekeepers. These spinning neutron stars beam radio waves with metronomic regularity, their rhythms so precise they rival atomic clocks. At first glance, they seem like FRBs polar opposites, predictable versus erratic, steady versus fleeting. But here's the twist. Some scientists suspect certain repeating FRBs might be hyperactive pulsars having off days. They're usually steady signals interrupted by magnetic storms or quakes. The difference lies in their utility. Pulsars help us test Einstein's relativity and navigate spacecraft, while FRBs act as cosmic cartographers, mapping matter we can't see. Gravitational waves, ripples in space-time itself, offer another fascinating contrast. Detected by facilities like LIGO, they're born from collisions between black holes or neutron stars, events so violent they warp the fabric of reality. Like FRBs, they're transient and pack immense energy, but they carry fundamentally different information. Gravitational waves reveal the dynamics of massive objects moving at relativistic speeds, while FRBs encode details about the material they've traversed. Imagine the difference between feeling an earthquake and analyzing a beam of light that passed through the ground. One tells you about the quake's source, the other about the layers it traveled through. What makes FRBs truly unique is their dual role as both message and messenger. Unlike gamma-ray bursts that fade into obscurity or pulsars that repeat like clockwork, FRBs are cosmic multitaskers. Their brief flashes pinpoint extreme astrophysical events, while their distorted signals map the universe's invisible scaffolding. They're like a flashlight that not only illuminates hidden corners, but also analyzes the dust in the air as it passes. This versatility is why astronomers are racing to build tools like the Square Kilometre Array, because FRBs aren't just another oddity in the cosmic menagerie. They're a new lens for examining everything from galaxy formation to the nature of dark matter, proving that sometimes the most fleeting signals carry the deepest secrets. The next time you gaze at the night sky, remember, it's not just stars and planets up there. It's a cacophony of invisible signals, each with its own story, its own way of reshaping our understanding. And among them, fast radio bursts shine brightest as the universe's ultimate Swiss Army knife, unlocking mysteries we're only beginning to name. Behind every cosmic revelation, there's a team of brilliant minds staring at screens, tweaking algorithms, and chasing signals across the void. The discovery of the missing matter wasn't just a triumph of technology, it was a testament to human curiosity and grit. Take Jean-Pierre Marquardt, the astronomer whose pioneering work on fast radio bursts laid the groundwork for this breakthrough. For years, he and his colleagues faced skepticism. FRBs were dismissed as telescope glitches or atmospheric noise, their scientific value questioned. But Marquardt saw what others missed: the potential hidden in those millisecond flashes. His persistence paid off when his team's models predicted exactly how FRBs could reveal missing matter, turning a fringe idea into a cornerstone of modern cosmology. Then there's Keith Bannister, the engineer who designed the game-changing software for ASCAP. Picture him hunched over a keyboard in a remote Australian control room, writing code that could sift through terabytes of radio static in real time. His algorithm didn't just detect FRBs, it pinpointed their locations with surgical precision, allowing telescopes worldwide to swivel and capture follow-up data before the signals faded. It's the kind of innovation that blends engineering genius with astronomical intuition, proving that solving cosmic mysteries often starts with solving technical ones. And let's not forget the unsung heroes, the graduate students who spent sleepless nights monitoring telescope feeds, the technicians braving desert heat to maintain delicate instruments, even the citizen scientists who helped classify bursts through crowd-sourced projects. Science at its core is collaborative. When that 8-billion-year-old signal finally reached Earth, it wasn't just intercepted by a machine. It was decoded by a global network of passionate individuals, each adding their piece to the puzzle. What ties these stories together isn't just intellect, but something more profound: wonder. Astronomer Sarah Burke-Spoleyor once described tracking FRBs as listening for the universe's heartbeat. That poetic drive to understand, to explore, to connect with something greater fuels every late-night observation and painstaking calculation. These researchers didn't just find missing matter, they reminded us that science isn't about cold, hard facts alone. It's about people staring at the stars, daring to ask, "What's out there?" and then dedicating their lives to finding out. Their work echoes a truth as old as humanity itself. The cosmos doesn't give up its secrets easily. But when curiosity meets perseverance, when creativity cracks seemingly impossible problems, we don't just unlock the universe's mysteries, we rediscover our own capacity for awe. And that's a discovery no telescope can ever measure. Stories like the discovery of the missing matter do more than fill textbooks. They spark something profound in young minds staring up at the night sky. Picture a middle school student hearing how an 8-billion-year-old flash of light solved a cosmic mystery. Suddenly, astronomy isn't just facts and figures. It's a real-life treasure hunt with the universe as the map. Teachers who bring these breakthroughs into classrooms often describe that moment: the widening of eyes, the flurry of hands shooting up with questions. It's the kind of engagement that turns casual interest into lifelong passion. Consider the ripple effect. The same fast radio burst that rewrote our understanding of the cosmos might inspire a 10-year-old to build a makeshift radio telescope in their backyard. That child could grow up to design the next generation of space observatories, pushing boundaries we haven't even imagined yet. This isn't hypothetical. Many of today's leading astrophysicists trace their careers back to a single moment of wonder, whether it was watching a shuttle launch or holding a meteorite fragment in their hands. Cosmic discoveries have a unique power to bridge the gap between abstract science and tangible excitement. Educational programs are already harnessing this potential. Museums now feature interactive exhibits where visitors can catch virtual FRBs, while planetarium shows weave these breakthroughs into immersive narratives. Online platforms like Zooniverse let students analyze real telescope data, contributing to active research. The message is clear: you don't need a PhD to explore the universe's secrets. When a high schooler in Mumbai or Chicago helps classify a burst, they're not just learning, they're participating in the same scientific journey as professionals halfway across the world. But the impact goes deeper than recruitment. These stories teach a broader lesson about perseverance. For years, the missing matter problem seemed unsolvable until a clever combination of patience, technology, and teamwork cracked it open. That's a blueprint for tackling any challenge, scientific or otherwise. Students learn that even the biggest questions yield to curiosity, creativity, and collaboration. It's no coincidence that classrooms using FRB discoveries as case studies report spikes in critical thinking and problem-solving skills. The cosmos, it turns out, is the ultimate classroom. Perhaps most importantly, these moments democratize science. When a breakthrough makes headlines, it reminds everyone, regardless of background, that the universe belongs to us all. A child in a rural village with limited resources can gaze at the same stars as a Nobel laureate, pondering the same mysteries. That shared wonder is where future innovations are born. And as telescopes grow more powerful and discoveries more frequent, one thing's certain: the next generation won't just witness the golden age of astronomy. They'll define it. Fast radio bursts have all the ingredients for cosmic conspiracy theories: mysterious, powerful, and seemingly random signals from deep space. It's no surprise they've sparked wild speculation, from alien distress calls to interdimensional messages. But let's separate science fiction from scientific fact. While FRBs are undeniably bizarre, the truth about them is far more fascinating than any Hollywood plot. Take the alien hypothesis. When the first repeating FRB was discovered, some theorists jumped to the idea of extraterrestrial beacons, a cosmic SOS, or even a deliberate broadcast. But here's why that doesn't hold up. These bursts pack the energy of hundreds of millions of suns into milliseconds. No known technology, even theoretically, could generate that much power without vaporizing itself. Plus, FRBs come from galaxies billions of light years away. If it's aliens, they'd have had to engineer this signal 8 billion years ago, long before Earth even existed. Not exactly a practical way to say hello. Then there's the myth that FRBs are singular, unprecedented anomalies. In reality, they fit neatly into a family of extreme cosmic phenomena. Magnetars, for instance, neutron stars with magnetic fields so strong they'd erase your credit card from halfway across the galaxy, can produce similar, if less intense, radio bursts. We've even caught our own Milky Way's magnetar firing off an FRB-like pulse in 2020. This doesn't mean all FRBs come from magnetars, but it shows they're part of a continuum of known astrophysical violence, not supernatural outliers. Another common misconception, that FRBs are dangerous. Headlines sometimes sensationalize these bursts as potential threats, but the reality is oddly comforting. By the time an FRB traverses billions of light years to reach us, its energy has diluted to barely a whisper. The signal that revealed the missing matter, for instance, carried less energy than a microwave photon by the time it hit our telescopes. You'd absorb more radiation making popcorn than this cosmic cannonball could deliver. What about the idea that FRBs are rewriting physics as we know it? Here, the truth is more nuanced. While they've certainly challenged assumptions like how efficiently matter disperses across the universe, they haven't overturned fundamental laws. Instead, they've become precision tools for testing those laws under extreme conditions. For example, when researchers analyzed whether FRBs travel at exactly light speed as relativity demands, the bursts confirmed Einstein's predictions across cosmic distances we'd never probed before. So what do we still genuinely not know? Plenty. The biggest open question remains what exactly creates non-repeating FRBs. Magnetars explain some, but others might come from neutron star collisions, black hole jets, or phenomena we haven't even named yet. Even more puzzling are the rare bursts with bizarre polarization patterns, suggesting magnetic environments wilder than anything in our galaxy. And why do some FRB sources go silent for years, only to reactivate without warning? These aren't gaps in our knowledge, they're doorways to new discoveries. The beauty of FRBs lies in this balance between mystery and revelation. They're not alien messages or cosmic glitches, they're natural phenomena pushing the limits of our understanding. And as we decode more of their secrets, we're not just solving puzzles. We're learning how to listen to the universe's most dramatic whispers, one burst at a time. Capturing a fast radio burst is like trying to photograph a firefly's blink from miles away in a thunderstorm. That's the monumental challenge radio telescopes face every day. Modern arrays like ASCAP and CHIME aren't just single dishes pointed at the sky. They're sprawling networks of antennas working in perfect sync, transforming faint cosmic static into groundbreaking discoveries. Here's how these technological titans pull off the impossible. At the heart of ASCAP design is something called a phased array feed. Think of it as giving a telescope hundreds of eyes at once. While traditional radio telescopes can only observe one patch of sky at a time, ASCAP 36 dishes each cover 30 square degrees simultaneously, an area about 150 times larger than the full moon. This wide field view is crucial because FRBs flash without warning anywhere in the sky. It's the difference between searching for a needle in a haystack with a magnifying glass versus using a metal detector. But spotting the burst is only half the battle. To pinpoint its origin, ASCAP employs a technique called interferometry, where slight timing differences in how the signal reaches each dish allow scientists to triangulate its location with precision finer than a human hair seen from a kilometer away. Meanwhile, north of the border, Canada's CHIME telescope takes a radically different approach. Shaped like four enormous half-pipes stretching the length of a football field, CHIME has no moving parts. Instead, it relies on Earth's rotation to sweep the sky, processing incoming radio waves with custom-built supercomputers that analyze 10 trillion measurements per second. What makes CHIME revolutionary is its ability to detect FRBs across a vast frequency range simultaneously, from 400 to 800 megahertz. This broadband coverage lets astronomers study how the burst signal disperses across frequencies, the key to measuring how much matter it passed through. The real magic happens when these instruments collaborate. When CHIME detects a burst, it instantly alerts telescopes worldwide via systems like the VO Event Network. Within seconds, optical telescopes swing toward the FRB's coordinates, searching for afterglows or host galaxies, while X-ray and gamma-ray observatories scan for accompanying high-energy emissions. This global coordination turns what would be a fleeting curiosity into a multidimensional cosmic event. But the engineering challenges don't stop there. FRB signals are so faint that even the slightest interference, a passing satellite, a cell phone tower, even a faulty microwave in the observatory cafeteria can drown them out. To combat this, teams employ machine learning algorithms trained to recognize and filter out terrestrial noise, leaving only genuine cosmic signals. It's like trying to hear a whisper in a crowded stadium by teaching a computer to ignore every voice except the one you're searching for. What's astonishing isn't just that these systems work, it's how they're evolving. next-generation upgrades will see ASCAP and CHIME joined by even more sensitive arrays, like the upcoming Square Kilometre Array, which will combine thousands of antennas across 2 continents. Together, they'll form a net so fine-meshed that hardly an FRB in the observable universe will escape detection. And with each technological leap, we're not just building better telescopes, we're rewiring our ability to decode the universe's most elusive signals. Science has always been a global language, and the hunt for fast radio bursts is no exception. When that 8-billion-year-old signal was detected, it wasn't just a victory for one team or one nation, it was a triumph of international collaboration. Australian astronomers operating ASCAP pinpointed the burst's location. American supercomputers crunched the dispersion data. European telescopes captured follow-up observations, and researchers from dozens of countries analyzed the results. This wasn't just teamwork. It was a synchronized dance across continents and time zones, proving that unlocking the universe's secrets requires more than any single institution can offer. Consider how these partnerships work in practice. A telescope in Western Australia detects an FRB and instantly shares coordinates via the transient astronomical radio emission network, alerting observatories from Chile to South Africa. Within minutes, optical telescopes in Hawaii swing toward the target, while radio arrays in China tune to specific frequencies. Data flows into shared repositories where scientists worldwide, from seasoned professors to graduate students in remote universities, can access, analyze, and build upon each other's work. It's a model that turns competition into collective progress, where every breakthrough belongs to humanity rather than a single lab. The beauty of this system lies in its diversity of perspectives. An astrophysicist in India might approach signal analysis differently than a counterpart in Canada, leading to insights that neither would have reached alone. When researchers from Japan's Riken Institute collaborated with South Africa's Meerkat team to study repeating FRBs, they combined cutting-edge machine learning with unconventional radio astronomy techniques, yielding discoveries that revolutionized how we classify bursts. This cross-pollination of ideas isn't just helpful, it's essential for solving puzzles as complex as the missing matter problem. But international collaboration isn't just about pooling brainpower, it's about resource sharing on a planetary scale. No single country can afford to build telescopes covering every wavelength and every patch of sky. Canada's CHIME excels at wide-field FRB detection, while Europe's low-frequency array probes their polarization properties. The US-led Very Large Array provides high-resolution follow-ups, and Australia's Parkes telescope offers Southern Hemisphere coverage. Together, they form a global nervous system, each node compensating for the other's blind spots. Perhaps most inspiring is how these partnerships transcend politics and borders. In an era of geopolitical tensions, scientific collaborations remain some of the last truly neutral spaces, where researchers from rival nations work side by side, united by curiosity. The Square Kilometre Array, currently under construction across South Africa and Australia, involves engineers from over 20 countries, including nations with strained diplomatic relations. Yet at the telescope sites, the only flag that matters is the one stitched onto mission patches, Earth. This spirit of shared exploration extends beyond professional scientists. Citizen science platforms like Zooniverse let anyone with internet access help classify FRBs, while open access databases ensure discoveries benefit researchers everywhere, from Ivy League universities to underfunded institutes in developing nations. When that historic burst was analyzed, the resulting papers listed authors from 15 countries, a testament to how modern astronomy thrives on inclusivity. The lesson here goes beyond telescopes and data. Solving cosmic mysteries requires more than advanced technology. it demands a fundamental shift in how we approach knowledge. No single culture, no solitary genius, no isolated team can unravel the universe alone. But when we combine our strengths, when we share our tools and our questions, even the faintest signals from the edge of time become messages we can finally understand. And in that collaborative effort, we don't just discover the universe's secrets, we rediscover what humanity can achieve when we look up together. Every leap forward in space exploration comes with profound ethical questions, not just about what we can discover, but what we should. Take the search for extraterrestrial life. If we detect microbial organisms on Mars or Europa, do we prioritize studying them or protect them from contamination by our probes? The dilemma mirrors early debates in environmental science whether to observe nature untouched or intervene for knowledge. Some argue that scientific curiosity justifies any means, while others caution against becoming cosmic colonizers, repeating Earth's history of exploitation on a galactic scale. The Outer Space Treaty of 1967 laid groundwork, declaring celestial bodies free from national ownership, but modern missions test these boundaries. Private companies drilling asteroids for minerals or nations planting flags on the moon force us to ask, who regulates humanity's reach into the cosmos? Then there's the question of unintended consequences. Fast radio bursts and other cosmic signals might hold keys to universal mysteries, but what if decoding them requires technologies that alter pristine environments? Radio telescopes listening for alien signals already flood frequencies with human-made noise, potentially drowning out the very phenomena we seek. It's akin to using floodlights to study fireflies. Our tools might obscure the truths we're trying to uncover. Astronomers now advocate for radio quiet zones, shielding portions of the spectrum from interference, a reminder that even passive observation carries responsibility. The ethics of exploration extend to cultural preservation, too. When spacecraft land on celestial bodies, they leave behind debris, lunar modules, rovers, even human ashes sent as memorials. To future generations, these sites may hold historical significance. Should we designate landing zones as cosmic heritage sites, protecting them like UNESCO safeguards Earth's treasures? The Apollo 11 landing site, with Neil Armstrong's footprint still preserved in the moon's dust, raises poignant questions about our footprint on the universe. Perhaps the most profound ethical layer lies in messaging. Projects like METI, messaging extraterrestrial intelligence, deliberately beams signals into space, hoping for contact. Critics liken this to shouting into a dark forest without knowing what listens. If life exists beyond Earth, do we have the right to initiate communication without global consensus? The debate splits scientists. Some see outreach as an evolutionary milestone, while others warn of risks we can't foresee. Balancing progress with prudence isn't new, but space magnifies the stakes. Every discovery reshapes our place in the cosmos, and every mission sets precedents for generations to come. The challenge isn't just reaching farther, it's ensuring that as we unravel the universe's secrets, we honor the humility and wisdom that true exploration demands. When astronomers chase cosmic mysteries like fast radio bursts, they're not just unlocking secrets of the universe, they're sparking innovations that reshape life on Earth. Consider the humble Wi-Fi router in your home. Its technology traces back to radio astronomy research in the 1970s, when scientists developing methods to analyze faint celestial signals inadvertently created the foundation for modern wireless communication. That's the hidden ripple effect of fundamental research. Breakthroughs designed to study distant galaxies often become tools that revolutionize everyday life. The hunt for FRBs alone has pushed computing to new frontiers. Processing their ultra-fast signals requires algorithms capable of sifting through mountains of data in real time, a challenge that's driven advances in machine learning and neural networks. These same techniques now power everything from medical diagnostics to fraud detection, proving that software designed to decode cosmic static can also save lives and protect bank accounts. Even the ultra-precise timekeeping needed to measure FRB dispersion has trickled down, improving technologies like GPS synchronization and high-frequency stock trading. Then there's the materials science revolution quietly unfolding in telescope labs. To detect faint radio waves, engineers must eliminate interference from heat, vibration, and even the telescope's own electronics. This pursuit has led to superconducting materials that operate at higher temperatures, cryogenic cooling systems more efficient than industrial refrigerators, and ultra-lightweight composites now used in everything from aircraft wings to prosthetic limbs. The same carbon fiber panels that keep radio telescopes stable in desert winds are being adapted to make electric cars lighter and more energy efficient. Perhaps the most surprising economic impact lies in energy innovation. Solar panel technology owes its existence to space research. Early satellites needed efficient ways to convert sunlight to power. Today's photovoltaics still borrow from designs first developed for orbital telescopes. And as astronomers push to build ever larger arrays like the square-kilometer array, they're driving demand for renewable energy solutions to power these remote installations, accelerating progress in solar storage and smart grid technology. But the true value transcends individual inventions. Astronomy fosters a problem-solving mindset that permeates entire industries. The collaborative software platforms created for global telescope networks have become blueprints for multinational research projects in medicine and climate science. The data visualization tools developed to map cosmic webs now help epidemiologists track disease outbreaks. Even the project management techniques honed by coordinating observations across time zones are being adopted by tech startups and disaster response teams. This isn't just about spin-offs, it's about cultivating a culture of ambitious exploration. When societies invest in deciphering 8-billion-year-old light pulses, they're not just buying telescopes. They're funding the kind of curiosity that leads engineers to ask, what if? And entrepreneurs to ask, why not? The economic returns might be unpredictable, but history shows they're inevitable. After all, the same society that wonders about the cosmos is one that keeps inventing the future. The moment fast radio bursts entered the scientific lexicon, they sparked a creative supernova in the arts, proof that the universe's most enigmatic signals don't just belong to astronomers. Take Icelandic composer Hild Jorgardnadottir's haunting orchestral piece, FRB 121102, which translates the first repeating bursts radio waves into shimmering strings and dissonant pulses. By sonifying the signal's dispersion pattern, she turned raw data into an auditory journey, letting audiences feel the 8-billion-year voyage of that cosmic scream. Meanwhile, visual artists like Rafik Anadol feed FRB datasets into AI algorithms, generating swirling nebulae of light that pulse in sync with the burst's erratic rhythms, installations where viewers stand immersed in the ghostly echoes of distant galaxies. Science fiction, always quick to mine the cosmos for metaphor, has embraced FRBs as plot devices rich with possibility. Liu Cixin's The Three-Body Problem sequel imagines them as alien quantum communications, while indie games like Observation weave bursts into narratives of AI awakening. What fascinates creators isn't just the science, but the mystery. FRBs embody the thrill of the unknown. They're modern-day celestial sirens, luring storytellers to explore themes of isolation, connection, and humanity's tiny place in the cosmic web. Even Marvel's Eternals movie featured an FRB-like signal as a harbinger of celestial upheaval, proving these phenomena have pierced mainstream consciousness. The trend extends beyond fiction. At the Griffith Observatory's planetarium, visitors don VR headsets to ride an FRB from its explosive origin through intergalactic gas clouds, a visceral merger of art and astrophysics. Podcasters like Cosmic Vertigo dramatize burst discoveries as audio thrillers, complete with the tense moments when researchers first spot a signal. Even tattoo parlors report surges in clients requesting minimalist FRB waveforms inked alongside dates of personal significance, turning cosmic transience into intimate permanence. What makes this cultural moment remarkable is its reciprocity. Just as artists borrow from science, astronomers now collaborate with creators to visualize complex concepts. The team that detected the missing matter FRB worked with graphic novelists to illustrate their findings, resulting in a comic that's equal parts research paper and space opera. Museums host FRB listening parties where attendees reinterpret radio data as jazz improvisations or electronic remixes. It's a feedback loop of inspiration, the raw wonder of discovery fueling artistic expression, which in turn makes the science accessible to new audiences. Perhaps the deepest impact lies in how FRBs reshape our collective metaphors. Once we spoke of the universe's silence, now we know it crackles with radio chatter. The idea that a millisecond burst can traverse eons mirrors modern anxieties about digital messages lost in time, how a tweet or text might outlast civilizations. In galleries, concert halls, and novels worldwide, these cosmic flashes have become mirrors, reflecting not just the universe's secrets, but our own yearning to connect across the unimaginable void. The hunt for fast radio bursts is accelerating into uncharted territory, with scientists preparing instruments that could make today's discoveries look like mere preludes. Imagine telescopes so sensitive they could catch an FRB erupting every few minutes, not just from distant galaxies, but from our own cosmic backyard. That's the promise of projects like the Deep Synoptic Array in California, where engineers are deploying a new generation of dishes with receivers 10 times more precise than current technology. These upgrades aren't just incremental, they're revolutionary, designed to detect bursts so faint they'd have been invisible a decade ago. And it's not just about quantity. By capturing FRBs across a wider range of frequencies, from ultra-low radio waves to near-optical bands, researchers hope to finally crack the code of what generates these cosmic flashes. But the real game changer lies in coordination. Astronomers are weaving a global web of observatories from the icy plains of Greenland to the deserts of South Africa that can collectively monitor the entire sky in real time. The goal: to catch an FRB the moment it happens, triggering instant follow-ups across every wavelength imaginable. Picture this: a burst is detected by a radio telescope in Australia, and within seconds, gamma-ray satellites, neutrino detectors, and gravitational wave observatories all pivot toward its origin. This multi-messenger approach could finally link FRBs to specific cosmic events, whether it's a magnetar's tantrum or a neutron star collision. Some teams are even experimenting with AI-driven systems that predict where and when repeating bursts might flare up again, turning guesswork into precision science. The next frontier isn't just observing FRBs, it's creating them in the lab. Using ultra-powerful lasers, physicists are simulating the extreme magnetic fields thought to power these bursts, recreating microsecond-scale versions of cosmic conditions impossible to study otherwise. These experiments could reveal whether magnetars really are the engines behind FRBs, or if something even stranger like cosmic strings or primordial black holes might be lurking in the data. Meanwhile, theorists are running supercomputer simulations that model how FRB signals distort as they traverse different cosmic environments, essentially building a decoder ring for the universe's hidden matter. What's most exciting isn't the tools themselves, but the questions they'll let us ask. Could FRBs reveal variations in the fundamental constants of nature across billions of light years? Might they help us detect the cosmic web's faintest filaments, or even probe the nature of dark energy? Every new burst carries the potential to upend our understanding, and with telescopes like the Square Kilometre Array coming online, we're on the verge of a golden age of discovery. The universe has been sending these cryptic messages for billions of years. Now, finally, we're learning how to read them. You might think unlocking the universe's secrets requires a fancy degree or access to billion-dollar telescopes, but here's the beautiful truth: the night sky doesn't discriminate. Some of astronomy's most exciting discoveries start with ordinary people, teachers, students, retirees peering through backyard telescopes or sifting through data on their laptops. Take the case of amateur astronomer Andrew Gray, who spotted a never-before-seen glow on Jupiter using nothing but a 6-inch telescope, or the volunteers with NASA's Planet Hunters project who helped identify exoplanets that professional algorithms missed. These aren't outliers, they're proof that cosmic exploration is a team sport where anyone can score. Dive into citizen science platforms like Zooniverse, where you can classify galaxies from your couch using images from the Hubble Space Telescope, or join the SETI at Home initiative, lending your computer's idle processing power to analyze radio signals for signs of extraterrestrial intelligence. Projects like Backyard Worlds comb through satellite data for nearby brown dwarfs, failed stars lurking in our cosmic neighborhood, and they've already credited over 40,000 volunteers with co-authoring scientific papers. The barrier to entry isn't expertise, it's curiosity. Even if you can't tell a quasar from a comet, tutorials and community forums guide you step by step, turning beginners into contributors faster than a supernova explodes. If hands-on observation is more your style, amateur astronomy clubs offer a gateway to the stars. Organizations like the American Association of Variable Star Observers train volunteers to monitor pulsating stars, feeding data to professional astronomers studying stellar evolution. All you need is a modest telescope or even just binoculars. Many clubs loan equipment for free. The annual Great Worldwide Star Count invites participants to measure light pollution by counting visible stars in constellations like Orion, creating global maps that shape urban lighting policies. It's science that starts in your driveway but impacts research worldwide. For those who prefer screen-based exploration, apps like Sky Safari or Stellarium transform your phone into a portable planetarium, identifying celestial objects with a tap. Platforms like Telescope Live let you remotely control professional-grade observatories in Chile or Australia, capturing images of nebulae and galaxies without braving the cold or investing in pricey gear. And when you're ready to share the wonder, organizations like NASA and Night Sky Network provide toolkits for hosting public stargazing events, turning local parks into cosmic classrooms. The most inspiring part: many of these projects feed directly into active research. When you tag craters on Moon Zoo, you're helping plan future lunar missions. When you track meteors for the American Meteor Society, you're contributing to models that predict asteroid impacts. Every logged observation, every classified galaxy, becomes a pixel in humanity's ever-sharper portrait of the universe. So whether you're sketching Jupiter's storms through an eyepiece or training AI to recognize supernova, remember, the cosmos isn't just for scientists. It's for anyone who's ever looked up and wondered what's out there. And right now, somewhere in the vast dark, there's a discovery waiting with your name on it. There's something profoundly humbling about realizing that the atoms in our bodies, the stars above us, and even the vast cosmic voids between galaxies are all woven from the same invisible threads of matter. The discovery of those missing baryons isn't just a scientific checkbox, it's a mirror held up to our deepest questions about existence. For centuries, humans have looked at the night sky and wondered, are we alone? Is the universe chaotic or ordered? Now, we're answering those questions not with philosophy, but with pulses of ancient light. When astronomers confirmed that half the universe's ordinary matter was hiding in plain sight, they didn't just solve a math problem, they revealed a cosmos far more interconnected than we dared to imagine. Consider what this means for our understanding of reality. Those wispy filaments of gas between galaxies aren't just cosmic clutter, they are the scaffolding of existence itself, the channels through which matter flows to birth new stars and planets. We're not passive observers of this grand structure, we're products of it. Every element heavier than hydrogen in your body, the calcium in your bones, the iron in your blood, was forged in stellar furnaces and likely spent eons drifting through those very intergalactic currents before becoming part of you. This discovery collapses the false divide between out there and in here, showing us that the universe isn't just around us, it's within us. Then there's the sheer timescale. That 8 billion-year journey of the FRB puts human history into cosmic perspective. When that light pulse began its voyage, Earth didn't exist. The Milky Way was half its current age. And yet, against incomprehensible odds, we've developed the curiosity and ingenuity to intercept this message from the dawn of time. There's a quiet poetry in that, a species that's existed for less than a blink of the cosmic eye, managing to decode signals older than mountains, older than oceans, older than the very ground we stand on. It suggests something remarkable. The universe, through us, is beginning to understand itself. This revelation also reshapes how we think about mystery. For decades, the missing matter problem was a nagging reminder of how much we didn't know, but its solution didn't diminish the wonder, it deepened it. Instead of gaps in knowledge, we now see invitations to explore further. Those once invisible gas filaments challenge us to ask, what else are we overlooking because we haven't yet learned how to look? The universe seems to delight in hiding its secrets not behind locks, but behind lenses waiting for us to craft the right tools, the right perspectives, to bring them into focus. Perhaps most importantly, discoveries like this redefine what it means to be small. In a cosmos where we're dwarfed by unfathomable distances and time spans, it's easy to feel insignificant. But finding the missing matter flips that narrative. We're not just specks in the void, we're the part of the universe that can contemplate its own existence, trace its own origins, and marvel at its own complexity. That FRB didn't just carry data about gas clouds, it carried a tacit message: the universe is knowable, and in knowing it, we don't shrink, we expand, becoming witnesses to a story 13.8 billion years in the telling. So the next time you gaze at the stars, remember this: you're not just looking out into space, you're seeing the raw material of reality, the same atoms that built galaxies now rearranged into eyes to behold them. The missing matter was never truly lost, it was always part of the grand design, waiting for us to recognize our place within it. And if we've uncovered this much hidden structure in the cosmos, imagine what other connections might be waiting just beyond the edge of our understanding. Science thrives on skepticism. It's the immune system that keeps ideas honest. While the discovery of missing baryons through fast radio bursts has been widely accepted, some researchers raise thoughtful questions. Could there be other explanations for the dispersion patterns we've observed? Might our models of intergalactic gas be oversimplified? These aren't fringe objections, they're the necessary friction that sharpens scientific progress. One alternative theory suggests that what we're interpreting as diffuse gas could instead be numerous tiny, dense clouds too small to detect individually. Picture mistaking a swarm of gnats for a fog bank from a distance. The effect looks similar, even if the underlying structure differs. Another camp argues that our understanding of plasma physics might need refinement. The highly ionized gas between galaxies doesn't behave like the plasmas we can study in labs on Earth. Some simulations show that under certain magnetic field conditions, plasmas could create dispersion effects that mimic more matter than actually exists. It's like measuring ocean depth during a storm. The choppy surface might make the seabed appear deeper than it is. These critiques aren't dismissals of the FRB findings, but calls to deepen our investigation. Historically, this is how science always moves forward. When the cosmic microwave background was first detected in 1965, some physicists initially dismissed it as mere instrument noise or pigeon droppings on the antenna. Only through rigorous debate and repeated verification did it become the cornerstone of Big Bang cosmology. Similarly, the current FRB consensus won't stand because scientists all agree. It will endure because every plausible alternative has been tested and found wanting. Teams are already designing next-generation experiments to distinguish between the mainstream model and its challengers. What makes this process beautiful is its built-in humility. Scientists publishing counterarguments today might provide the crucial insights that lead to tomorrow's breakthroughs. The astronomer who first questioned the missing matter calculations could be the same person who later discovers an even more profound cosmic truth. This isn't contradiction, it's how knowledge evolves. Every dissenting voice that withstands scrutiny makes our understanding more robust, while those that don't still serve as valuable stress tests for prevailing theories. The key distinction lies between healthy skepticism and dismissal without evidence. While some alternative theories merit investigation, others ignore overwhelming data-like claims that FRBs are atmospheric phenomena despite their proven extragalactic origins. Science navigates this spectrum by demanding testable predictions. A valid critique must suggest specific observations that could confirm or refute it, not just point out gaps in current knowledge. This ongoing dialogue reveals something profound about how we explore the universe. Truth isn't decided by votes or authority, but by nature's relentless arbitration through experiment and observation. Whether studying 8-billion-year-old light pulses or debating dark matter, the scientific method remains our most reliable compass, not because it always points north immediately, but because it's self-correcting. Every question asked, every alternative proposed is another step toward seeing the cosmos more clearly, even when the answers aren't what we expected. The universe doesn't keep time by human clocks. While we measure progress in grant cycles and academic semesters, cosmic revelations unfold on timescales that dwarf our lifespans. The 8-billion-year journey of that fast radio burst is more than a scientific curiosity. It's a masterclass in patience. Consider the astronomers who dedicated entire careers to the missing matter problem, poring over telescope data year after year, knowing they might never live to see the answer. Their persistence mirrors the very signals they study, brief flashes of insight separated by long stretches of uncertainty, each one building toward a revelation. This isn't unique to astrophysics. History's greatest discoveries often come from those willing to embrace the grind. Take the hunt for gravitational waves predicted by Einstein in 1916, but not detected until 99 years later. Generations of physicists refined LIGO mirrors to sense vibrations smaller than an atomic nucleus, all for a signal lasting less than a second. Or consider the Voyager probes, launched in 1977 with instruments designed by engineers who knew they'd never live to see their craft leave the solar system. These endeavors share a common thread: the courage to plant trees whose shade you'll never sit under. What's remarkable is how the cosmos itself models this persistence. Stars spend billions of years fusing hydrogen into heavier elements, knowing nothing of the planets or life their ashes might one day form. Galaxies collide over eons, their slow motion dances reshaping entire constellations. Even the humble neutrino, so elusive it can pass through a light year of lead without interacting, teaches us that significance isn't measured by immediacy. The universe operates on a timescale where every breakthrough, every connection requires waiting beyond what feels reasonable. For scientists chasing FRBs, this means embracing failure as data. Early attempts to detect missing matter using X-rays or ultraviolet light fell short not because the ideas were wrong, but because the tools weren't yet sensitive enough. Each dead end wasn't a stop sign, it was a signpost narrowing the path forward. When radio telescopes finally caught those elusive distortions in FRB signals, it wasn't luck. It was the inevitable result of iterative curiosity, of questions asked again and again with slightly better instruments each time. There's a deeper lesson here for anyone facing a daunting challenge. The missing matter wasn't found by a lone genius in a eureka moment, but by a chain of thinkers passing the baton across decades. It's a reminder that progress often hides in plain sight, waiting for the right combination of technology and tenacity to reveal it. Whether you're studying the cosmos or pursuing any long-term goal, the universe seems to whisper the same truth: keep showing up. The answers aren't just coming, they're already on their way, racing toward you at the speed of light. Scientific breakthroughs often wear two faces, one of careful planning, the other of sheer cosmic serendipity. The detection of that 8-billion-year-old fast radio burst wasn't just a victory of cutting-edge technology, it was also a stroke of celestial luck. Consider the odds: a pulse of energy lasting mere milliseconds, traveling across interstellar voids for longer than Earth has existed, arriving precisely when our planet happened to spin into alignment with a telescope array in the Australian outback. Had the burst arrived 12 hours earlier or later, it would have sailed silently past, its secrets lost in the eternal dark. This dance between preparation and chance isn't unique to astronomy. History brims with discoveries where luck played matchmaker to curiosity. Alexander Fleming's accidental contamination of Petri dishes led to penicillin. The cosmic microwave background, the afterglow of the Big Bang, was discovered when radio astronomers stumbled upon persistent static they initially blamed on pigeon droppings in their antenna. Even the first gravitational wave detection in 2015 hinged on a lucky coincidence. Both LIGO detectors happened to be operational during a rare black hole collision after years of upgrades. Science, it seems, loves to reward those who stay ready for the universe's unexpected gifts. What makes the FRB discovery special is how it showcases the delicate interplay between human ingenuity and cosmic randomness. The Australian Square Kilometre Array Pathfinder didn't just happen to be pointed in the right direction. It was meticulously designed to monitor vast swaths of sky, increasing the odds of catching fleeting signals. The algorithms that spotted the burst weren't lucky. They were painstakingly trained to recognize patterns in noise. Yet without that perfect alignment of preparation and happenstance, the missing matter might still be hiding in plain sight. This duality raises a profound question: how much of scientific progress is deliberate, and how much depends on the universe's whims? The answer lies in how researchers cultivate what French microbiologist Louis Pasteur called the prepared mind. Luck favors those who build the tools to recognize it, whether it's a telescope array listening for cosmic whispers or a lab notebook ready to document unexpected mold growth. The FRB's discoverers didn't just get lucky, they engineered an environment where luck could meaningfully collide with curiosity. Perhaps the most beautiful aspect of this story is how it democratizes discovery. While billion-dollar telescopes play a crucial role, some FRBs have been spotted by amateur astronomers poring over publicly available data. The universe doesn't discriminate between PhDs and hobbyists when it sends its serendipitous signals. Every time we point a telescope skyward or peer through a microscope, we're rolling the cosmic dice not in hope of easy answers, but in readiness for the moment when preparation and chance conspire to lift the veil on reality's deepest mysteries. The next great breakthrough might already be racing toward us, a photon or radio wave halfway across the universe. Whether it finds us ready depends not on luck alone, but on our willingness to keep looking and our wisdom to recognize the extraordinary when it finally blinks into view. Theoretical physics often feels like navigating by starlight, working from mathematical clues to chart courses through uncharted cosmic territories. Decades before telescopes spotted those faint filaments of intergalactic gas, equations on blackboards had already outlined where the missing matter should be. Cosmologists studying the afterglow of the Big Bang noticed a discrepancy. The amount of ordinary matter predicted by their models didn't match what telescopes could see. It was as if the universe's ledger showed funds that hadn't materialized in any observational account. The numbers were clear. About half the expected baryonic matter was unaccounted for, hiding somewhere between the glittering islands of galaxies. What's remarkable isn't just that theorists identified this gap, but how they did it. By reverse engineering the universe's early moments, they calculated how much hydrogen and helium should have formed in the first few minutes after the Big Bang. These primordial elements became cosmic breadcrumbs, marking where the rest of the matter ought to be. Simulations then mapped how this material should have evolved, flowing into the vast cosmic web we see today. The models painted a vivid picture: diffuse gas threading the voids between galaxies, too faint to spot with conventional telescopes, but leaving gravitational fingerprints on surrounding structures. Theorists even predicted the gas's temperature, a scorching 10,000 to 1,000,000 degrees, explaining why it wouldn't emit visible light. Yet for all their elegance, theories alone couldn't close the case. Science demands evidence, and for years, this hypothetical matter remained just that, hypothetical. Early attempts to detect it using X-ray telescopes glimpsed only the densest clusters, like spotting mountaintops poking through clouds while missing the valleys below. The breakthrough came when astronomers realized they needed a new tool, one that could sense the invisible by how it bent the cosmic signals passing through. Enter fast radio bursts, nature's backlit probes. When that 8-billion-year-old pulse finally streamed into detectors, it didn't just confirm the theorists' predictions, it showcased the beautiful symbiosis between abstract math and empirical discovery. This dance between theory and observation is the heartbeat of scientific progress. Einstein's general relativity predicted gravitational waves a century before LIGO detected them. Paul Dirac's equations hinted at antimatter before cloud chambers revealed positrons. In each case, the universe seemed to whisper its secrets first to those fluent in the language of mathematics, then waited for technology to catch up. The missing matter saga adds a crucial twist. Sometimes the data doesn't just confirm the theory, it refines it. Those FRB measurements revealed the gas filaments were slightly clumpier than simulations suggested, prompting cosmologists to tweak their models of cosmic evolution. What makes this collaboration so powerful is its built-in checks and balances. Theories without observational grounding risk drifting into abstract fantasy, while observations untethered from frameworks can become disconnected facts. Together, they form a self-correcting system where each discovery sharpens the questions we ask next. The missing matter wasn't found by accident. It was uncovered because theorists dared to say, "Look here," and observers built tools capable of looking. Now, as new mysteries like dark energy and quantum gravity loom, this partnership grows ever more vital. The same interplay that revealed the universe's hidden scaffolding may one day decode its deepest enigmas, not through guesswork, but through the patient dialogue between imagination and evidence. After all, the cosmos writes its truths in many languages, the stark poetry of equations, the silent testimony of light, and the patient detectives who learn to translate between them. That ancient pulse of light, traveling across 8 billion years of cosmic history, did more than solve a missing matter puzzle. It rewrote the rules of how we explore the universe. Think about the sheer improbability of this moment, a burst of energy from the dawn of time, perfectly aligned with our planet's position in space, intercepted by technology that didn't exist a generation ago. It's like the universe handed us a key just as we finished building the lock. This discovery transcends astronomy textbooks. It proves that the answers to our biggest questions are often hidden in plain sight, encoded in the faintest signals, waiting for the right perspective to reveal them. For decades, scientists stared at the same starry canvas, searching for missing matter in all the obvious places. It took an unassuming radio flash to show them they'd been looking at the picture upside down. Those wispy filaments of gas between galaxies aren't just cosmic filler, they're the connective tissue of the universe, the invisible rivers that shape everything from star formation to galactic evolution. What's truly humbling is how this breakthrough exposes both our ingenuity and our limitations. On one hand, human curiosity built machines sensitive enough to catch a millisecond whisper from across the cosmos. On the other, we're reminded that the universe still holds mysteries we haven't even thought to question yet. If half the ordinary matter was hiding in plain sight for billions of years, what else might be lurking just beyond our current understanding? The story of FRB 202200610 isn't just about physics, it's a testament to persistence. Generations of astronomers kept searching for those missing atoms, refining their tools and theories, even when the answers seemed perpetually out of reach. Their dedication mirrors the journey of that light pulse itself, an unwavering trajectory through time and space, determined to deliver its message no matter how long the voyage. As we stand on the shoulders of this discovery, the horizon stretches infinitely before us. New telescopes like the Square Kilometre Array promise to catch hundreds more of these cosmic messengers, each one potentially holding clues to questions we haven't even learned to ask. Will they reveal new layers of the cosmic web, help us finally grasp dark matter, or uncover phenomena we can't yet imagine? The universe has shown us once again that its greatest gifts come wrapped in mystery. That 8-billion-year-old flash didn't just illuminate missing matter, it lit a path forward for exploration. Every time we decode one of space's enigmas, we don't just find answers. We discover better questions, and somewhere out there right now, another signal might already be racing toward us, carrying the next piece of the puzzle. If these cosmic detective stories fascinate you, join the conversation below. Share which universe mystery you think will crack next: dark energy, alien life, the nature of time itself. Don't forget to follow for more journeys to the edge of understanding. Because in this vast, whispering cosmos, every discovery is just the beginning of a deeper